of rectangles that we're thinking about adding up, which would be, in this case, n. Meaning the area of the first rectangle, so thinking length times width, I already have delta x there, but the height of that first rectangle would be f of delta x. And since we now can say that delta x is equal to 2 over n, I can also write that as f of 2 over n times 2 over n. So that can represent the area of the first rectangle. Why don't you take a second? Why don't you fill in the blanks there for the area of the second rectangle, and then compare what you have with somebody sitting near you.
I did 2 delta x, I mean 4 over n. Wait, what is 2 over n?
I think because you still have the same delta x for the...
Oh, the length is still, I don't know, other than
Okay, did you check in with somebody sitting near you? Risha, you're looking quite awake today. What did you get for filling in your blanks? So f of blank times delta x would represent the area of the second rectangle.
2 delta x.
Mm-hmm. Okay, and that would end up being equal to f of blank. What do you think, Dennis?
4 over n.
4 over n, 2 times delta x, which is 2 over n, so that would be 4 over n, and then times 2 over n, since that's still delta x. So that would represent the area of the second rectangle. So remember, lower sum, right? This is the lower sum, is adding up the areas of n number of inscribed rectangles. Okay, so each of those products represents the area of an inscribed rectangle. So we can fill in these blanks with what we got for the first rectangle and the second rectangle. So f of 2 over n times 2 over n, and then f of 4 over n times 2 over n. And then if we look back at our picture, how can we represent the area of the last rectangle on this interval? F of 2, right? Because we're choosing the right endpoint for finding the height of each of the rectangles. So f of 2 would be the height of that last rectangle times 2 over n. Okay, conceptually, do we understand what we're doing? Based on what we've written out, have we followed how we landed here? Yes, okay.
So I should have asked this earlier, but for the f is decreasing on the interval, why is it inclusive or not, or is it like, why is it brackets and not parentheses?
Oh, because we're calculating the area on the interval from 0 to 2. So 0 and 2 are endpoints. And so the function values are just included there. Okay, so I would like you to next try this on your own, or if you need to talk to somebody who's sitting near you, you can do that. Go ahead and represent this sum in the sigma notation. So fill in the blanks here. Okay, so that sum, I is equal to 1, and then we're adding, so we're starting when I is equal to 1 and then adding up n number of rectangles. We would have the rule for each rectangle be f of, Nathan, can you help me here?
F of I times 2 over n and 2 over n and I times 2 over n.
Say that one more time. F of,
I times 2 over n.
yeah, so, or 2, you could write that as
Or
2i over n, yeah. Okay, and then times
2 over n.
2 over n, the width. Right, so this right here represents the height of each of the rectangles, and then this represents the width of each of the rectangles. Well, since we know the rule for f, we can go ahead and replace f of 2i over n with 9 minus 2i over n squared. Okay, and now we're going into some algebra. So if we square 2i over n, that'll be 4i squared over n squared.
Wait, sorry, how do we know x is 2i over n? Why are we doing that?
Okay, so because we're finding the height for each of the n number of rectangles by evaluating f starting at 1, right? So if we plug in 1, f of 2 over n would be the height of the first rectangle. And we saw that, right? Like we thought about what the first one would be. And then we would move on to 2, letting I equal to 2. So then that would be f of 4 over n would be the height of the second triangle. We let I equal to 3, and we'd have f of 6 over n as the height of the third triangle, and so on. So because we're thinking about for finding the heights of each of the rectangles, evaluating the function, I'm just replacing f of 2i over n with the rule of the function. Yeah, with 2i over n substituted in. So this still, if this is helpful, this still represents height of each rectangle, and this still represents the width. Okay, and then we're just simplifying it. So then next we can think about distributing the 2 over n. And then that lands us at 18 over n minus 8i squared over n cubed. Which, if we remember from 4.2 part 1, we have that property for sums, the addition subtraction property, where we can think about splitting up the sum. Now remember, n represents what again? Number of rectangles that you're adding up. So like we could think about plugging different values in for n. Like if we wanted 4 rectangles, n would be 4. If we want 6 rectangles, 12 rectangles, right? We would be plugging those values in. So essentially n is a constant, which is why we can think about pulling out 1 over n and pulling out 8 over n cubed, because we are thinking of n as being a constant. So treat n as a constant. And that's because it's the number of rectangles. That's for this guy and this guy. Okay, and then hopefully you recognize, hey, we know how to evaluate this sum and this sum. We can replace the sum from 1 to n of 18 with what? 18n. And then also one of the formulas that I'm giving you is whenever the rule for the area of each rectangle is I squared. That is n times n plus 1 times 2n plus 1 over 6. And then for thinking about how this could simplify, notice this n can cancel with one of these n's. And then we can also factor out a 2 in the numerator and denominator to cancel. So that then we have 4 over 3n squared. And we can think about multiplying out the n plus 1 times 2n plus 1. So that's 2n squared plus 3n plus 1. Where we can distribute and we would have 18 minus, what is that? That'll be 8/3. So minus 8/3, and then minus 4 over n minus, 4 over 3n squared. And then we can combine the constant. So 18 minus 8/3 ends up being 46/3. Minus 4 over n minus 4 over 3n squared. So what we've just come up with is a function for this particular function that can calculate the lower sum on this specific interval from 0 to 2. So you can plug in different values for n, which would represent like different numbers of rectangles that you would want to use in order to approximate the area. Remember, the lower sum, it's adding up all the inscribed rectangles. So it's kind of based on that number of rectangles, it's the smallest approximation you could get for the area. Versus if you're calculating upper sum and you're picking the maximum function value on each subinterval, that's going to be the largest approximation that you could get for that number of rectangles on the interval. Okay? Do we understand what this is? So like if I told you to calculate the lower sum for 6 rectangles, you could plug 6 in for n, tell me what that value is, and then that would be the sum of the 6 inscribed rectangles on that interval. Are we okay? Okay.
Would you describe this as dark magic or light magic?
There's no magic here.
Bro.
No magic done. Now, you can consider this a little bit of magic because I don't want to go through the entire process again. I don't think you guys do either. But you could for coming up with the rule for the upper sum.
Oh wait, we can plug
So
in
the
like an in for n.
upper... Stick with me. Stick with me. Trust the process. Okay, so we could take the upper sum, and the upper sum is 46/3 plus 4 over n. You can call it magic if you would like, but like you would follow a similar process for coming up with this. So this is the rule for the upper sum for this particular function on this interval. So this would be choosing, well, instead of using the right endpoint, because the function's decreasing, you would be using the left endpoint of each subinterval, the function value that corresponds for the height of each rectangle.
Wait, so what if we just be approaching?
No, can't we just, no,
No.
stick with me.
Is there a general rule?
Stick with me. Stick with me. I know, just stick. We're going to get there, just keep with me.
You're what is it called?
Okay. So now using your graphing calculator, you can also do this in Desmos if you prefer. Go ahead and type in the rule. It'll be in terms of x into your calculator. So like in y sub 1, y sub 2, and you're going to fill in this table. Now, if you're using your graphing calculator, you want to make sure that you have it. Can I see your calculator? Oh, have we not used this in a while?
No.
So you want to make sure that you have it set so that you can type values into your table. So you would hit second window, and you want to have for the independent variable ask highlighted, so that then after you type in the rules for your functions, you can go to the table and you're able to type in different values for x. Okay. Now you don't want to use the handy dandy fraction bar on your calculator here, because then it's going to give you the different values in the table as a fraction. You do want to use grouping symbols. If you are using Desmos, you can call up, oh, it deleted it. You can call up, so I'm going to type each of these in, and you can call up the table for each one by using the little settings thing. So I'm going to have lower sum is, where is my lower sum? There it is.
Why do you need upward and lower?
Trust the process, Janice. Trust the process. Think about it.
I don't know.
Think about it.
Value, like,
Short for upper bound, and then low
It's- yeah,
short
it's-
for
it's-
lower bound.
yeah, it's like kind of like Calc is short for like calculator,
AP calculus.
but also AP calculus and AP calculus AP. It has multiple meanings to one word.
Okay.
AP Calc. Is that all knowledge?
Dennis, does anyone ever call you Den?
Short.
Oops.
Okay. Are we serious right now? No.
Well, we can start now.
I mean, if you want to annoy me, I guess you do, but like, you know, that's pretty mean.
That was a diss.
Like, that's kind of mean, I'm not gonna lie.
Okay, so we don't so much care about what the functions look like right now, but we do care what they are trending towards as we think about plugging in larger and larger values. So to pull up in Desmos the table for each one, you probably already know this, but somebody reminded me how to do it this morning. You can hit that settings, and then you can call up the table for each one, and then you can just type in the values that you're looking for.
Oh, wow.
Why
So,
do you
like-
need error?
I bet
She
it's
doesn't
I bet it's how you used your oh, you have your stat plot on for some reason. Oh, why'd you go in N in terms of N?
Well, I thought you're supposed to use it.
Oh, but when you're graphing in here, you're graphing in.
No.
Oh,
way.
right. That makes sense.
Oh, and also this will turn out for order of operations. This would end up being 4/3 times x.
Oh, okay. Go also the table.
Yeah, you press plus and then you do table.
But there's like the same exact numbers. Can it like?
Think about it, Dennis.
I
Think
know.
about what's
I thought
happening.
about it. You were just gatekeeping.
I don't think why.
I don't know. Is that mean? Is that like not?
No, it's really accurate use of the word actually.
For
your
I know. I just want to say it, but like you're gate. I can't say it. I don't want to ruin the fun experience of math for others. Even though. Yeah.
After you filled in your table, you can talk to somebody next to you about what you think is happening.
What?
Is that blue one or something?
I mean, wait, hold on. Would you rather have blue as the lower sum represented or red represented as the lower sum?
R short for
I think blue.
Yeah, blue. That's the same for me.
Is that gonna like?
Yeah, because it's like yeah, like blue's cold.
It's cold.
I don't.
That's a good argument.
And if you're curious, you can type in larger values. Like if I put 10,000 in there.
Wait, it's the
many decimals you just present in?
And if you're curious, you can put 100,000 in, or just keep putting larger values
We're
in.
just gonna get closer to the asymptote.
Yeah. That's what okay.
Right? If you're zooming out, what we're doing is we're zooming out in the positive direction.
Locally linear.
Well, we're talking about as n goes to infinity.
Infinitely linear.
Okay.
Define infinity.
Did we get similar values in our tables?
Yes. At first define infinity.
So again, the values that we're plugging into those two functions represents the number of rectangles. So like looking back at this table, so n represents the number of rectangles. So like this would be the approximated area for 100,000 rectangles on the interval from 0 to 2. Like this would be the approximation, the lower sum approximation for 10,000 rectangles.
That's kind of cool.
Then we have the upper sum approximation for 5,000 rectangles. The upper sum approximation for 10,000 rectangles. So as we think about adding more and more rectangles, what does it seem like the lower and the upper sums are approaching?
15 and 1/3.
46 over 3.
Okay. Oh, yeah. Or we could say 15.3 repeating. Okay. So in conclusion, we can say both the lower and upper sum have a limit as n approaches infinity. So we can slap our limit notation on there and say the limit as n approaches infinity of lowercase s of n is equal to the limit as n approaches infinity of capital S of n. And that limit is 15.3 repeating, or 15 1/3.
Wait, what did you mean?
So remember, let's review. The lower sum is for a number of rectangles. So if you pick a number of rectangles, it's the smallest approximation you could get for that number of rectangles. Like the smallest value. For upper sum, for that specific number of rectangles, it's like the ceiling. It's the largest value that you could get, like the largest approximation of the area you could get for that set number of rectangles. So what this is saying is if we think about adding up infinitely many rectangles, that the lower sum and the upper sum end up being the same value.
Okay.
That's the conclusion.
Yeah.
Which
I don't
means,
know why we both. Like, we could just
so
end
if
up
we
with one.
thought about adding up,
Just one.
If we thought about adding up infinitely many, infinitely skinny rectangles, that's going to, which is what we just did, that's going to give us the actual area under the curve, bounded by the curve and the x-axis on this interval. So this area is 15.3 repeating.
So every time we do one of these, if we want to find the approximate area, we need to do all of this stuff.
Well, we have to do it the hard way before we do the short parts.
Why do we do
We are
this short,
we are building our conceptual understanding of like where we're going with
Wait, but do we
this.
do the short
Why do we
before
both?
the quiz?
That's what I asked.
Maybe
No.
we'll get to that.
No.
but- Like,
Okay, so this is these limits are the actual area of the region. but isn't it exciting? We have a way to calculate the actual area.
It is pretty, yeah, it is pretty.
Isn't that cool?
It's kind of like.
You guys, isn't that crazy to think about? By taking the limit of that, you are essentially adding up infinitely number of areas of rectangles.
Yeah.
Cool.
That's kind of.
I think it's infinitely cool too.
Okay. What are we doing?
Okay,
Wait, hold on, Ms. Dorset. Like, why do we need both the upper and the lower? Because, like.
look, hold the thought.
Oh, are we serious?
Hold the thought. I love that you're like thinking about like where we're going with this. But let's like think about where we could be going, Dennis. Let's think about where we could be going with this, not just couldn't we just do this? Why do we need this? There's a reason. There's obviously a reason.
Mr. Wells, a professional rage baiter. Now we have a professional.
Is that what I'm doing? I'm
Are
rage
you like,
baiting you?
no, professional gatekeeper.
Okay. So let's come up kind of with a more
Cool down,
formal,
cool down.
generalized way of calculating the area of a plane region. So remember, we're talking area. We will be able to eventually extend this. This whole section is about area, so we're thinking about the function being positive. Now, what we've just seen is that those two limits are equal to each other, right? The limit, so adding up infinitely many inscribed rectangles, areas of inscribed rectangles, and adding up infinitely many circumscribed rectangles. We ended up with the same value. So really, we could think about for finding the height of each rectangle, because remember, essentially you're adding up this like insanely skinny strip, or finding the area of this insanely skinny strip. You technically could think about choosing any value on each subinterval for finding the height of each rectangle, right? And because we've seen when we add up infinitely many of the inscribed rectangles, it's equal to adding up infinitely many of the circumscribed rectangles. So it does not matter what value you choose, so whether left, right, midpoint, somewhere that's just anywhere on each of the subintervals, you can choose any value for coming up with the height of each of the rectangles. So I can come up with this more generalized formula that represents the sum of the areas of n number of rectangles. Are you following me here? So this is thinking about just choosing, and doesn't have to be the same for each rectangle, but just choosing some value that's on each subinterval for coming up with the height of each of the rectangles. So delta x, still, and I think it's helpful to kind of interpret what each part of these mathematical statements are. Delta x still represents the width of each rectangle. And then these would represent the heights of all of the rectangles. In sigma notation, we can represent this sum like so, where f of c sub I represents the height of each rectangle, and delta x represents the width of each rectangle. So their product represents the area of each rectangle. And this is the sum, this whole thing would be the sum of the areas of all the n number of rectangles. That's annoying. So if we think about taking the limit as n approaches infinity of this sum, it's going to end up being equal to the limit as n approaches infinity of the lower sum, which is equal to the limit as n approaches infinity of the upper sum, which is the area of the region. We could even do a little squeezy-weezy theorem to help us, like, with proving that. Were you?
Can we? Yeah, I was thinking.
Yeah, so like thinking about the lower sum based on n number of rectangles, right? The lower sum will be less than or equal to the sum of n number of rectangles where you're choosing like randomly values on each subinterval for finding the height. Which would be less than or equal to the upper sum. So then if we think about taking the limit as n approaches infinity, so adding up infinitely many rectangles for each of these sums, like we already saw that these two limits end up being equal to each other. Therefore, this limit would also have to end up being equal to the actual area
Oh,
by the
I
squeeze
see.
theorem.
Okay. Okay. I mean, wait, the only thing that I don't. Oh, and. Oh, I see. Oh, I see. Okay. Never mind. I see what you did there.
Okay. So assuming that those two, the limit of the lower sum, limit of the upper sum both exist, and they're equal to each other, they would be, then that limit also has to be equal to the actual area. So you guys are going to be able to use this new limit definition for calculating area. Delta x, you guys already know this formula, right, would be b minus a over n. If you are choosing the right endpoint of each subinterval, that allows you to, when you come up with your sum, have I start at 1. So for c sub I, which is like what you're replacing here, right? So evaluating your function at, for coming up with the height of each rectangle. You want to use c sub I being equal to a plus delta x times I. That's going to give you the right endpoint of each of the subintervals. Okay, so I'm going to talk you through, this is all already written out. Claire, are you with me? Do you need a quick stretch break or something? We're all falling asleep right now. Everyone stand up and stretch.
Yeah, we do so. Can we like? I don't know why. It's like sleepy gas.
Well, we're in the mid. I can't. I want to keep going, but we can take a quick stretch. We're not fully leaving. We're just stretching.
Yo, let's play some ball. Wait, ball
This is ball short court.
Yes.
What ball?
Yeah.
Basketball.
No.
That reminds me of what's his sweatshirt? What is it?
Yes, it is. You make it whatever it is. You make what it is.
All right, you guys, let's do it. We can do it.
It means what you want it to mean. Every word
I know I've been jibber-jawing a bunch, but I'm almost done jibber-jawing at you.
Almost done. Professional game.
Okay, so now we are going to look at, I have this all typed out for you already, so you just have to follow along. So calculate the area bounded by f of x equals 9 minus x squared, which I believe is the same function as earlier, but different interval from 1 to 3. So delta x would end up being 2 over n, right? So 3 minus 1 over n. C sub I, So what the function is being evaluated at for finding the height of each rectangle is going to be 1, right? So that's A, plus delta x times I. So plus 2I over n. So setting this up, area is going to be equal to the limit as n approaches infinity of the sum from 1 to n of f of 1 plus 2I over n times 2 over n. Right? So this is height of each rectangle, width of each rectangle. Right? Height of each rectangle, width of each rectangle. Okay? We know the function, the rule for the function. So thinking about substituting 1 plus 2I over n into the function. And then it's algebra, right? So we're thinking about expanding. So multiplying this out to go from here to here. Distribute the negative. And then we're distributing the 2 over n in here.
Wait, what is CI again? I kind of know.
It's what you're evaluating the function at to come up with the height of the rectangle. So for simplicity, we're just thinking about, so that we can use the summation formulas that I am giving you guys, we're always thinking about using the right endpoint of each subinterval.
Okay.
So it would be A plus delta x times I. Okay, so then you thinking about that property for the sums where we can split up this up into the difference of these sums, okay? Again, n we are able to treat as a constant, so like I can pull 1 over n out here, 8 over n squared out here, 8 over n cubed here. Is everyone staying with me here? And then we are set up so that we can use the formulas that I'll be providing you guys with. So you guys know how to evaluate this, thank you Gauss, and this, Frederick.
I don't know the last name.
He was no gatekeeper, huh?
He was not.
Okay. So we can see like we end up with 16n.
Sport.
N times n plus 1 over 2. And then n times n plus 1 times 2n plus 1 all over 6. Okay. So from here we want to simplify that expression. And we're able to simplify down to here. So this is just, I multiplied this out, although you don't technically have to do that. This I just pulled the 4 out from, okay? But if we're thinking about taking the limit as n approaches infinity of 16, it's just 16. Limit as n approaches infinity of n plus 1 over n. You can think n behavior model, you can think back to pre-calculus and be like, oh, same degree in the numerator and denominator. So like this would go to 1. And then the limit as n approaches infinity of this would be 2. Right? Your n behavior model would be 2n squared over n squared, which is 2. So that limit ends up being 16 minus 4 minus 8/3, which is 28/3. So that's the actual area. Of f of x on the interval from 1 to 3. Okay. We're going to take, everyone put your pinky up on your right hand. We're going to line up longest pinky to shortest pinky on your right
What
hand.
kind of? Are you serious right now?
It's up to you whether you want to count your nail or not. You choose.
Okay, that's cheating.
Okay,
That's cheating.
ready, set, go. Longest pinky to shortest pinky.
Back the line.
I'm sorry,
Back the line. Alright.
Whoa, hey. Oh, no.
Whoa. Cheating allegations.
What? I'll let you decide.
Right.
Where's the longest pinkies?
Longest pinkies are over here.
Cheating allegations.
Yours is longer.
Wait, I haven't really
My nail counts.
Oh my god, that's cheating.
I know. To the back.
Wait, I think we should do.
I had them do pointer fingers earlier.
Ref.
Didn't. I think people
Get
do
this.
this.
Get this out of here. That's tech.
No.
Mine is
You're the only person.
No, it's like this, like, you know what I mean? And that's
Camilla has a pretty long nail too. It's not that serious.
Camilla's really
Do
tiny.
we count nails or not?
It's up to you.
No, because I asked the person said you can use the nail, right?
Wait, yeah, you're longest.
Do you still have the shortest pinky even with your nail?
Damn. Yeah, that's kind of.
Yeah.
Yeah.
That's a pretty.
Yeah.
Is that rage bait? It might be
Alright.
rage bait.
1, 2, 3. 1, 2, 3. 1, 2, 3. So let's go 1, 2, 3. You guys are calculating the area.
One. Where's one?
Ones are always here, twos are always there, twos are always here.
Yay,
So you're calculating this area on the interval from 0 to 1.
Would you rather?
Okay.
Bring back that window a bit or have
Like,
47?
One minus 0 over n.
Sounds
Over n. That's right?
Yeah.
Okay, what is it?
That's, yeah,
One.
Change in x.
delta x.
Wait, what? Oh, delta x. Oh, yeah. Whatever, yeah, okay. Yeah.
Is it? Alright. 1 minus 0.
Then ci. Wait, what now? Equals, how do you calculate ci?
It's a plus
Oh.
I delta x. I don't know if a or I are actually.
Wait.
Yeah, I don't
No,
know.
I is just
I.
I. And a is like isn't a?
Oh,
No, a is 1. Wait, what's
a
that?
is 1, yeah, a is 1.
Wait, are we sure?
No, a is 0,
Oh,
sorry.
yeah. 0?
Yeah, why is 8 0?
So it's I over n.
Because it's 0 to 1 is the end equal.
Oh, yeah, okay.
I over n, so then area.
We should do the A
No.
thing.
Oh, I see.
Here, I'm playing
Yeah,
it. This
right.
is what we do.
Yeah,
So just I over
First
n.
thing is we did this, right? Oh my god.
Okay.
Now we have
Writing,
the
that's
CMI
OD.
thing, which is A.
What's
A is
OD?
the
That's
O
OD,
0.
yeah.
So it's 1 minus 0.
Cursive, for cursive. Like, I can't tell. That's like enchanting.
CMI equals 0. Yeah.
Enchanting
plus
table.
What is he saying?
R of X.
Yeah, he's writing an enchanting table.
What is
So A is 0.
I can't tell anything.
1 minus
Like,
0. So see like
actually, I can't tell. That's
plus I, and then we just found
So
out
it's
that,
out
right?
at I
We
equals
did not.
0.
No,
right?
I.
Yeah. I equals.
Okay, so then area, we do this
Also-
weird thingy.
And then it's
F of, is it F?
it's ci times whatever
As n goes to.
Wait,
Oh,
isn't
wait,
it 1
oh,
over
F
I
of-
over
oh, it's
over n?
F of-
I over n, no?
f of I over n.
Yeah.
And then you do
Just times
times
Yeah. Times. Yeah.
Wait, I don't know how James does
Wait.
I'm getting a eraser.
Wait. I think
Go
it's
eraser board,
aside
yeah.
from
Yes,
the
what
CI.
the-
Actually, 1 over n is outside the
You
CI.
put whatever you want for CI,
Oh wait.
you put that in there.
No, yeah.
Oh yeah, that makes sense.
Right, it makes sense because you're
Oh,
wait. Like what is this?
What's
What is
a
this
constant?
Thank
enchanting
you,
thing?
Claire.
Like is that like a curse or spell? That's a spell, bro.
Okay, so yeah, so you do
You
that.
just casted a spell in math
I'm
class.
very happy for you,
F
Jeff.
of.
Like come on, what are we doing?
Yeah, parentheses around all of this,
Whatever, you should stop making fun. It's kind of.
It's okay, I appreciate
You can take it.
Okay, times.
Okay. Did you
Perfect.
split it out?
So now, I'm not really sure.
Oh,
what
we
we do.
substitute the x.
Wait,
So
what?
then we go x squared plus 2.
Wait.
Remember that the unit is
Oh, because okay.
Yeah,
Okay.
whatever you want.
Okay.
And then we go separate.
Wait, let's take this out. Look at this. Well,
Yeah,
1 over
so
n is
ask
constant.
for
equations.
Oh.
Really?
Yeah.
You seem to, your life goals seem to be to insult Claire with a chance.
Oh, because it's a constant, right? Yeah.
I remember what I said.
Yeah,
I was
Saturdays,
in
you
the
said a
morning.
lot.
I still have the letters that were said in like 3rd or 4th grade or something.
Okay, we can probably
Who's that? I
get
actually
a
still
square
remember those letters.
I'm very good
Square
handwriting
twelve
for
plus
like
two is
first.
well, okay, so now, I think we can do a limit of that, which would be just anything, so like just,
So then it's,
So I'm like, this is-
so we would have,
Yeah, and he
plus
says two that part.
what is,
no, you can't take it out of
oh, yeah, no.
It might be Frederick.
Okay, fine, no, yes, you can.
Where did you guys come from?
Okay, hold on, fine. You guys are just like one step behind, okay. Not in a bad way. I'm just 2 steps ahead. Frederick's just one step behind, I'm 2 steps ahead, right? I'm just 2 steps ahead. Can I have a little better writing position? This is really, it's really.
Dennis is 2 steps ahead, I don't know what to do.
Hold on, wait, let me cook, okay, let me do that, and I equals 0, 2, does this make sense? Is what I'm trying to do here.
Yes.
Okay, there you go, that's good, okay. Okay, so, what's the equation now?
Well, you have to distribute the square.
Yeah, that's exactly what I'm trying to do. You guys wanna help me out with this? Like, what?
2 steps
Okay,
ahead.
now do you understand this concept of like go back a step?
Right.
Like, I went back a step over here, so I'm not 2 steps ahead anymore. I'm on like normal speed.
No.